Hello, my name is Jacob St. Martin, and I am the team leader and mechanical design lead for the University of Virginia's Big Idea Challenge team.
Hello, my name is Rex Serpi. I'm a third-year student studying computer engineering, and I am the embedded systems engineering lead for the team.
Hello, my name is George Wilkes. I'm a PhD in electrical engineering, and I was the lead on the photovoltaic cell and the laser system.
Hi, my name is Julia Rudy, and I'm a third-year computer engineering student, and I worked on the gimbal tracking code.
Hi, my name is Kirti Radhakrishnan. I'm a fourth-year computer engineering student, and I'm the battery systems lead.
Hello, my name is Edward Lee. I'm a second year at the University of Virginia. I'm an electrical engineering major, and I was the data representation lead.
Hi, my name is David Chen. I am a second year at the University of Virginia studying electrical and computer engineering, and I'm the thermal and radiation lead for the UVA Bell team.
Near the lunar South Pole, there are craters that never receive sunlight. These regions, called permanently shadowed regions, or PSRs, remain at average temperatures of 100 Kelvin or lower, and contain water ice and other volatiles due to the low temperatures. This ice is so important because it can be studied for scientific knowledge, used to support lunar habitation, or used for electrolysis into liquid oxygen fuel. This habitation and fueling capability is a key component to space exploration. However, due to the lack of sunlight, incredibly cold temperatures, and large exploration areas, traditional power systems cannot be used for exploratory equipment. BELL is a power beaming solution to address the future power generation needs for scientific exploration of the lunar permanently shadowed regions. Wireless power transmission is of particular interest for PSR missions because it avoids the harsh PSR environment that hinders traditional powering systems. Nuclear energy is very costly and raises potential safety concerns. Laying a wire of 10 kilometers or more would be heavy, expensive, and difficult to install. And microwave power beaming has too large of a beam divergence to operate at large distances. With BELL, power can be beamed from the continually sunlight illuminated rim of the crater using a high-efficiency, high-powered laser to a distant asset in the interior of the permanently shadowed region. A beam scanning system and a quadrant arrangement of photodetectors are used to locate and track the asset. An automated gimbal orients the solar cell to face the beam, allowing the laser power to be converted back into electrical energy for use by the equipment. A small portion of light is reflected back by retroreflectors and is used for laser tracking. This innovative optical tracking system eliminates the need for multiple radio communication towers. Power beaming has a number of important applications, the first of which is the exploration of PSRs. In addition to this, power beaming and optical tracking could be used to distribute energy from one localized source to a number of targets. This could be used on Earth in areas where power lines have been disrupted, or in space where having power lines or multiple power sources would be costly and inefficient. Lastly, the military is looking into power beaming for integration into defense systems. Shown here are the subsystems of BELL. These subsystems were developed and tested individually before integration. Each subsystem will now be explained by the team lead of the system.
A high-power laser source is needed to beam energy from the semi-perpetually illuminated rim of the lunar crater to a photovoltaic array mounted on the asset. In this regard, we compared diode and fiber laser systems and their various trade-offs as seen in the table. Typically, diode lasers are capable of higher electrical to optical conversion efficiencies since fiber lasers rely on a two-step conversion process, but they have relatively higher divergence since they are not a single mode. Additionally, while the cooling requirements are typically more challenging for diode lasers, they still have a lower size and mass when compared to fiber lasers. Laser thermal requirements on the moon were difficult for us to assess terrestrially, however lasers are widely used for space applications today, so this problem has already been addressed by various space agencies. As shown in A, we went with an IPG DLM 100-975, fiber-coupled direct diode laser operating at a wavelength of 975 nanometers at a maximum power of 105 watts, with a wall plug efficiency of 45% and a divergence of 10 milliradians. As shown in B, the beam profile is nice and uniform due to the multimode fiber, and has an approximate full width at half maximum of 41 millimeters at a distance of 5 meters. The power density was measured using a thermopile sensor and a 1 square centimeter aperture, as shown in C. The measured power density matches the specified power for a given current perfectly if the 41 millimeter full width half maximum is used for the laser diameter. We use beam conditioning optics to increase the beam size, reduce beam divergence, manipulate the beam direction for searching and tracking, and to retroreflect the beam back along a path parallel to the incident beam to return it to the photodiodes housed concentrically around the collimator head. The beam expander, shown in A, is a 3x Galilean expander, which is needed to prevent internal focusing, which becomes problematic with high laser powers, and are also more compact than Keplerian expanders. The beam diameter is increased from 8 to 24 millimeters, which conversely reduces the divergence from 10 to 3 milliradians. 2 perpendicularly mounted servomotor mirrors steer the beam in X and Y, which is used for searching and tracking the retroreflective target. In the video, you can see how the mirrors oscillate as the increasing diameter spiral is drawn. This is the pattern we use for object searching. Retroreflectors are used to return the beam on a parallel path to the incident light, which will be sent along the same optical path back to 4 photodiodes, located concentrically around the collimator head for the laser. In C, you can see the difference in the illumination on the photodiodes when the beam is off target versus on target, showing how the light is picked up by the detectors. To convert this laser optical power back into electricity, multi-junction metamorphic indium gallium arsenide cells on germanium substrates are used. These cells are specifically designed for laser beaming by Spectralab Incorporated. These cells have a peak spectral response in the 900 to 1100 nanometer range, with a specific spectral response of 0.68 amps per watt at our laser wavelength of 975 nanometers. Current voltage measurements, shown in A, were taken of the solar cell under increasing laser illumination intensity. Because our source meter was current limited to a maximum of 1 amp, an aperture was used to assess the current density output of the cell at full laser power. While this unfortunately reduced the maximum voltage of the measurement from 640 millivolts to 540 millivolts due to shadowing portions of the cell, an impressive current density of 5.19 amps per square centimeter was measured. This suggests that our cell efficiency is 41% at full laser power, with a max power output of 3.22 watts for a single cell. As shown in B, a single cell was mounted on a copper block using silver paste to assist with thermal dissipation under the intense laser illumination. In C, you can see the laser illuminated spot on the cell with the probes on the anode and cathode of the cell. 4 of these cells were interconnected in series to increase the overall voltage from the receiver to around 2.5 volts. This was done by using silver paste and silver foil to interconnect the front-facing anode bus bars of the one cell to the rear cathode on the subsequent cell, until 4 cells were connected in series. Again, due to current limitations of our source meter, the current voltage measurement of our array was only possible at 19 watts of input power. But an impressive 32.6% array efficiency with a maximum output voltage of 2.45 volts was measured. Using a multimeter to measure the open circuit voltage and short circuit current of the array at the full 105 watts of laser power, the output power and efficiency was estimated using an identical fill factor to be 9.93 watts with a power conversion efficiency of 31.4%.
Pictured on the slide here is the remote control car that was used as the rover for the Bell proof of concept. While Bell could be used to power stationary assets, the rover shows how a moving system could also be wirelessly powered in the moon's craters. The rover holds several key subsystems. First, towards the front is a dual-axis gimbal, which is used to center the laser beam onto the receiver. Secondly, mounted on top of the gimbal is the photovoltaic receiver used to convert the optical power to electric power. Finally, mounted on the body of the rover is the custom maximum PowerPoint tracking PCB that is connected to the receiver and charges the rover's battery. As you can see in this video, we realized that if the mount for the photovoltaic receiver on the rover was stationary, there's no guarantee that the laser would always be able to lock onto the cells, even if the tracking system was able to detect the reflected light from the rover. Our solution was to design a mount that could adjust its position so that even if the rover was driving in the opposite direction, the mount could alter its position until it was facing the laser. Here is a picture of the gimbal, which consists of 2 motors to control the yaw and pitch angles. The mounting plate on the gimbal is made out of copper to dissipate any heat generated, and the gimbal itself is also covered in aluminum tape to shield it from the laser. Retroreflective tape was placed along the 360 degrees of rotation of the mount, so that the laser will always lock onto an area the gimbal can adjust to. There is also a microcontroller that is continuously measuring the output of the receiver. As long as the microcontroller doesn't detect the laser on the receiver, the gimbal will rotate 360 degrees. As soon as the microcontroller senses illumination on the cell, the gimbal will then stop spinning. It will then incrementally move by 1 degree in yaw and pitch while monitoring the output from the cell. If the new position receives less illumination, the gimbal then returns to its original position and tries to move in another direction. The gimbal repeats these steps until it finds a position where the incident light is centered on the receiver.
The laser collimator, beam expander, and galvo all require precise alignment and a rigid mount in order to achieve the desired effect. To get this alignment, significant mechanical design work was done. As seen in the image here, the optical breadboards were mounted to aluminum extrusions. Then, the 3D printed parts and XYZ stage were secured to the optical breadboard. This setup allows for a high level of customization, where components are secure but can quickly be adjusted as needed. In order to ensure perfect alignment, the entire system was modeled in SOLIDWORKS. This 3D modeling allowed us to test different configurations of components and to be certain that all of the components would come together properly before ordering or 3D printing parts. The video shown here is a rendering of the system made in SOLIDWORKS that demonstrates the path of the beam as it travels through the system. First, the beam is fired from the laser collimator, which gives the beam a uniform profile. After this, it goes through the beam expander, where the beam is expanded from 8 mm to 24 mm, which helps to reduce beam divergence over large distances. Then the beam travels to the galvanometer, which is a system of 2 motor-controlled mirrors that direct the beam to the target. The galvanometer allows for rapid scanning of the beam that is necessary for searching and tracking. The beam then travels to the target, where the solar cell and retroreflectors are located. Here, the majority of the beam is converted into electricity, while a small portion is reflected back to the galvanometer, through the beam expander, and back to the laser collimator, where there are 4 photodiodes which measure the reflected light, allowing for tracking.
The laser tracking system is powered by a pair of STM32 F413ZH microcontrollers. By working in parallel, these microcontrollers allow the system to track and charge targets of interest. At the simplest level, the microcontrollers accomplish this task by moving the mirrors in a scanning galvanometer. By moving the X control mirror, the beam can be shifted from left to right, and by moving the Y control mirror, the beam can be shifted up and down. By controlling these 2 mirrors, the system can move a beam around a space while reading changes in the photodiode sensors in order to search for targets. As the galvanometer microcontroller articulates the mirrors, the laser beam is directed to different locations within the system's field of view. Simultaneously, the sensor microcontroller is reading values from the photodiodes at a rapid rate. When the scanning beam encounters a reflective target on a rover, light is reflected backwards along the exact same path that it traveled along to reach the target initially. This means that the light will travel right back towards the galvanometer. When the reflected light arrives at the galvanometer, the mirrors reflect it back into the beam expander. As the reflected light travels backwards to the beam expander, it begins to diverge very slightly. And finally, as the reflected light travels from the beam expander to the laser housing, it expands just enough to illuminate the photodiode sensors which are mounted around the laser. In this way, the sensor board is able to detect a change in the sensor readings and infer that the system has encountered a target. In order to maximize tracking speed and minimize latency when a target is detected, the two microcontrollers, or MCUs for short, are used in a parallel computing configuration. The scanning MCU's sole task is to send instructions to the galvanometer, which designate the next location for the beam. It spends its entire computing capacity sending instructions to the galvanometer as quickly as possible, and it has tables stored in its system memory to increase the rate that it can send these instructions. Similarly, the sensor microcontroller spends the entirety of its computing power reading changes on the photodiodes and making decisions about whether or not a target has been detected. The system follows a rather simple algorithm to search a space for a reflective target. The galvanometer MCU directs the beam to a number of distinct points along a circular path, pausing just long enough at each point to allow the sensor board to check for a target. If no targets are found along this path, the size of the search circle is increased and the process is repeated. As soon as a target is detected, the sensor MCU alerts the galvanometer MCU, which locks onto its current location. The galvanometer remains locked onto its location until the target moves out of the beam path, at which point the reading on the sensor microcontroller drops below a given threshold and it instructs the galvanometer MCU to begin searching again. The Galvo MCU begins its search from the previous target lock. This way, if the target has only moved a small distance, the system can find it again quite quickly. As a result of the fast processing speed of the microcontrollers, the search paths, and in particular the first few paths in a search sequence, can be scanned rapidly. As a consequence, targets can be quickly located after only moving a small distance. As seen in the video, the system is able to locate the target almost immediately after it moves out of the beam path. This means that rovers or other remote devices could be charged as they operate, possibly even while moving around craters or other regions of interest. This could significantly extend the lifetime of each charge cycle and allow longer periods of exploration before a long charging time is required. Once the system has locked onto the rover, it can increase the beam intensity and begin the charging phase. The charging system was designed to effectively utilize the output of the solar array to charge and power the system. This charging system performs several important duties. First, it converts the low voltage, high current output of the solar cell into a higher voltage, lower current output, which is suitable for charging the lithium polymer battery that powers the rover. Secondly, it serves as a maximum power point tracker for the array, which ensures high efficiency from the array for a wide range of laser intensities. Finally, it ensures safe charging of the lithium polymer battery, preventing undervoltage and overvoltage conditions, and also maintaining a safe charge current. In order to accomplish these tasks, a printed circuit board was designed, manufactured, and populated. This PCB consists of a number of stages to fulfill the design requirements. First, the output of the solar panel enters a boost converter integrated circuit, which produces a fixed 12-volt output. Next, the board contains a LiPo charger integrated circuit, which using the output of the boost converter, intelligently delivers voltage and current to the battery charging output. This integrated circuit prevents the board from overcharging the battery or allowing the battery to undervoltage. It also restricts the maximum charge current. Finally, the board contains a power mux. This component allows the system to utilize power both from its own battery systems and the solar array. If either power source drops out, the power mux allows the functioning source to continue delivering power to the rover. Using its combination of software and hardware, Bell is able to effectively and efficiently enable laser tracking and power delivery. We're confident that this system can enable the exploration of PSRs and other regions previously inaccessible to current technologies.
In terms of data representation, as the laser is beamed to the solar cell on the gimbal, the power generated from the charging printed circuit board into the battery can be measured by finding the voltage in the current. As the battery is charging, its percentage power is demonstrated using an LED indicator circuit, and the power generated is demonstrated using an LCD monitor connected to an Arduino Nano. The purpose of this representation of data is to properly show the application of the power beaming and its ability to supply power to the rover. To determine the percentage of the battery charging state and demonstrate it visually, a battery LED indicator circuit was designed and created. This circuit used the LiPo battery's characteristic curve to determine the voltage of the battery at specific percentages. In this case, 20, 40, 60, and 80% was used. Since the LiPo battery is a 2-cell battery, the threshold voltages shown in the chart were multiplied by a factor of 2 to determine the true battery percentage relative to the voltage. 4 comparators were used at threshold voltages 6 volts, 6.8 volts, 7.1 volts, and 7.3 volts for the aforementioned percentages. When the battery voltage was above the threshold value, an LED was lit up to indicate if the battery charging level percentage is greater than the threshold percentages.
To also show the battery's voltage and current values at any given time, an LCD module display was used. This LCD monitor is controlled by an Arduino Nano. Since the Arduino Nano can only read voltage values up to 5 volts and the battery is a 7.4 volt LiPo battery, the voltage of the battery had to be stepped down using a voltage divider, and this stepping down had to be refactored into the software implementation of the LCD to display the correct voltage. The current value displayed is the current coming from the solar charger printed circuit board into the battery connection port. This measurement can be found by measuring the voltage drop across 2 test points on the printed circuit board and dividing it by the resistor value in between. A simple but effective use of Ohm's law. The image shown is an integrated unit displaying both the LCD display and the LED indicator circuit as discussed earlier. As shown, the LCD display shows proper current and voltage levels of the battery using chosen test points on the printed circuit board. The LED indicator is also shown with 4 LEDs given the 4 battery percentage display values.
While power beaming and laser tracking have been independently demonstrated, Bell is the first reported system to integrate these components and the first to report an end-to-end efficiency. This slide shows a component view and operating principle of our overall system. The high-power laser system will emit light from the collimator. This light will then pass into a beam expander to increase the beam diameter, reducing beam divergence, which allows power beaming over larger distances. After leaving the beam expander, the light is directed using the 2-axis galvanometer scanner, which searches until a retroreflector is found, then locks onto the retroreflective target adjacent to the photovoltaic receiver. A portion of this light will be retroreflected back through the galvanometer scanner and beam expander, where it will land on 4 photodiodes used to measure the retroreflected intensity. 2 microcontrollers take the photodiode signal and utilize our algorithm to adjust the scanner mirrors to maintain a target lock. The remaining beam intensity is collected by the photovoltaic receiver, where it is boosted by our charge control board to provide power to the rover batteries. The gimbal housing the receiver is also capable of tracking the laser source through maximum power point tracking, so that the laser light remains incident on the photovoltaics. Here you can see all of our subsystems fully integrated into the complete system. These subsystems include the high-power laser, fiber collimator, beam expander, galvanometer scanner, photovoltaic receiver, tracking gimbal, charge control PCB, rover, and the quadrant detector. Not shown are the microcontrollers used for tracking. Each system was built and tested individually, then integrated into the whole system and optimized for performance. On this slide, we evaluate the component level efficiency for each of the subsystems involved in the power beaming process. Before the board transforms the power from the cells, our measured efficiency was 4.8%, but there are a variety of ways our system could be further optimized to easily bring the efficiency over 10%, with 18.2% being our system maximum theoretical efficiency. Additionally, our charge board only had a 63.4% measured efficiency, which resulted in further loss in overall efficiency. Here are the major sources of loss in our system and solutions which could address these problems. First, we used a low-cost laser system that had a maximum efficiency of 45%. However, there are commercially available laser systems at high power in our wavelength that have efficiencies exceeding 60%. Additionally, our laser beam profile was circular, resulting in poor illumination of our square PV array. This could easily be solved by using laser diode bars or other beam shaping optics, which can bring this near 100% efficiency if the beam shape and size are matched to the PV array. Next, the array efficiency was around 31% efficient, while a single cell was closer to 41%, primarily due to optical and resistive losses. Advanced interconnection methods such as wire bonding could reduce the series resistance in the array, while still maintaining a high shunt resistance and ultimate device efficiency. Lastly, our charge control board had a low efficiency as it was not optimized to maximize efficiency. If we optimize the board further, we could potentially boost power at 98% efficiency. Despite working in difficult circumstances, our team has made significant accomplishments. We demonstrated an integrated laser power beaming and laser tracking system, recorded the first end-to-end efficiency measurements for an integrated power beaming and tracking system, achieved all project goals on schedule and on budget, advanced the knowledge of power beaming, demonstrated a promising technology for NASA missions, and increased the technology readiness level of a power beaming and tracking system from 2 to 4. The next steps to making Bell mission ready include improvement of the overall system efficiency, demonstration of long-distance tracking, testing in the lunar environment, ruggedization and radiation hardening, and improvement of the technology readiness level. Given the success of this demonstration, we believe that with more development, Bell could be the key to driving exploration in the upcoming Artemis missions and beyond. We have faced many challenges throughout the process, primarily those related to the COVID-19 pandemic, but we believe that these challenges have made us stronger as a team. On behalf of the team and the University of Virginia, I would like to sincerely thank NASA and the NIA for giving us the opportunity to develop Bell. We would also like to give a special thanks to Stacy Dees, Victoria O'Leary, the judges, and everyone else who worked so hard to make this year's Big Idea Challenge a success and an incredible experience for our team.